think we'll get started. Good morning to everyone. My name is Vince Maraglia. I'm the Executive Director in the Office for Research at Rutgers University. I want to welcome you all to this joint scientific symposium between Rutgers and Tel Aviv University on the topic of trends in cybersecurity. Just a brief rundown of the program and a few housekeeping items. We're going to start this morning with a welcome from the Director of Homeland Security for the state of New Jersey, Jared Maples. Then we'll hear from the featured scientific speaker on the Rutgers side, Dr. Saman Zanuz. After that, Tel Aviv University VP of Research, Dan Peer, will introduce the featured speaker for Tel Aviv University, Eran Tromer. And then the Dean of the Rutgers School of Engineering, Thomas Farris, is going to moderate a Q&A session between our two featured speakers. In terms of the basics of the event, I want to encourage you all, as you listen to the speakers today, to ask questions actively through the Q&A button that you can see on the bottom of the screen. Use that Q&A button. As a question occurs to you, they'll be collated, and Dean Farris will be able to see those questions and potentially ask those as part of his moderating the Q&A session. So look out for the Q&A button on the bottom. So let's start by introducing the welcome speaker for today's event, Jared Maples. Director Maples oversees the New Jersey Office of Homeland Security and Preparedness. He was appointed on that role in June of 2017. He, among other things, in that role serves as the federally designated Homeland Security Advisor to the Governor of the state of New Jersey, Phil Murphy, and as a cabinet-level executive responsible for coordinating and leading New Jersey's counterterrorism, cybersecurity, and emergency preparedness efforts. Director Maples, before his duties in New Jersey, Director Maples had a long and impressive career in the federal government. He worked in the Department of Defense and also as an intelligence officer, Central Intelligence Agency. So please join me in welcoming Jared Maples. Director Maples.
Thank you, Vince. Appreciate the warm welcome and the opportunity to be here, and also want to extend my thanks to Dr. Farris as well. Rutgers has been an outstanding partner, and certainly want to thank Tel Aviv University. This is such an important initiative, and I can't tell you how excited that we're glad how we are to be a part of this, and have been. And I'll speak a little bit about that. Just want to take a few minutes to welcome everyone. Normally, we'd be welcoming you to the great state of New Jersey. Then in the age of coronavirus, we'll have to just welcome you online, but look forward to cleaning this pandemic up and hopefully meeting in person soon, maybe as early as next year, whenever we convene again. A couple of interesting points. I was actually in Israel. We were talking about it beforehand with Andrew Gross, who's on the call, Dr. Peer, amongst others. We did a state visit with Choose New Jersey about cybersecurity. It was one of the leading topics on that. And I think a lot of what we're talking about today really came to fruition from that meeting, that visit. In many respects, it feels like a lifetime ago. So much has happened, and yet it also feels like it was just yesterday. So kind of a strange situation. And of interest, I'm in Governor Murphy's cabinet, and that was the second visit we did. We went with Governor Murphy a couple of years ago, and again, similarly aligned with some artificial intelligence, cybersecurity, some of those other emerging technologies that Israel is so great at. Across the board, and certainly things that we'd like to think we're pretty good with Rutgers and some of our capabilities here in New Jersey as well. And that's why this marriage really makes a lot of sense. So I'm greatly honored to be here, and again, excited. I think it's a great thing for the state of New Jersey, and I think for our partners in Tel Aviv at the university and in the country as well. As Vince mentioned in my bio, we're responsible for leading and coordinating states' counterterrorism, cybersecurity, and emergency preparedness efforts. Sort of gets involved in everything of a negative nature that would happen to the state of New Jersey. We're somehow tied up in it and or leading it. And so it gives us a unique perspective on things. A couple of really interesting points about our cybersecurity presence. We're the first state in the United States to have an integrated information sharing and analysis center, an ISAC. That's modeled after the federal NCIC that's run out of DHS, Department of Homeland Security at the federal level. And other states are adopting that. They're moving towards that model, but we are the first and right now the only. I would anticipate we'll have some partners and colleagues in other states that'll be doing this shortly. As part of that, the cybersecurity role and mission is directly under Homeland Security. We're also the only state where that occurs. Most of the time it's under CIO or CTO position shops, or sometimes reporting straight through the National Guard or the governor's office. In New Jersey, we view it as a core Homeland Security mission. And it's important to how we can operate and share information federally from an intelligence perspective, both in and out, leverage some tools that aren't really there capability-wise from other components. And so again, that's another model we think is well on its way to making its way out to the other states, but we're proud that we're amongst the leaders. And I'll add in from the Jersey State side, the New Jersey State side, that Rutgers has been a key and vital partner to that, whether it be the research components, the School of Engineering, all the other aspects that we've talked about. We could not have done it without a lot of the academic research and partnership and capability from Rutgers. So again, proud and happy to be teaming up with you. When we went on that last trip to Israel, one of the really interesting meetings that I took personally, and we split off from the group, Andrew Gross was on from the NJ Israel Commission is on, we both met with Yigal Una, who's the National Cyber Directorate lead in Israel, and really had a great one-on-one, small group with him for over an hour, and just got a real good feel for what's happening in Israel on the ground. And I think he got a pretty good feel for what we're doing in New Jersey. And it's those type of relationships that help bond what's happening overall on this Zoom, and hopefully this growing relationship between the universities and our great states, and making sure that we're connected, because as a national leader in the United States and in Israel, an international leader in these areas, especially about cybersecurity, it really just makes sense. So I'll finish up a couple quick remarks for those of you who aren't aware of some of the things we do and the responsibilities wise. As far as the NJ Kick and what we do with cyber, we really focus heavily on information and intelligence sharing. That becomes a big key, again, both to the federal government and from the federal government, and then also out. So we like to think we're a capability builder. We build scale and scope out to entities that don't have it. So small municipal governments, for example, that don't have a robust cyber component, small and local and small and medium-sized businesses. A lot of those are being targeted right now by things like ransomware and directed attacks and DDoS, all these aspects that we know, I'd say know and love, but probably know and hate in the cyber realm. And we really try to scale that and get that intelligence down to there. We also conduct training statewide, exercises statewide, things like penetration testing. We offer all those tools. We secure the election system. Again, that's a little unique too. Homeland Security has a direct tie and partnership. I actually have a very senior level employee that reports directly to the Department of State in New Jersey for elections. And all year round, that's what he does and his team does is help secure the online presence in the election system. One of the interesting parts about my role too is I'm the Homeland Security Advisor to the governor, which is similar to the National Security Advisor to the president. And so I also have an advisory capability. So we bring to bear the cyber intelligence and knowledge, and also kind of know-how and how we build infrastructure and work through critical problems with technology, both private sector and public sector. And I become a key advisor in that role too. And then the final thing I'll add, and I'm kind of plowing through this, I know the most important stuff is after me, but I want to make sure I point it out, that we're also responsible for protecting the Garden State Network, which is our state IT infrastructure. And so there's an operational capability, and we use a variety of platforms, software packages, hardware, to really make sure that we're tight. And again, we like to think we're among the nation's leaders in that area in regard as well. But it is a key responsibility that it's not just an intel and information sharing environment like the federal government model. We've also incorporated an operations perspective and responsibility in securing what every single employee of the state of New Jersey and most of our citizens, although they probably want to kill us most of the time when it's with MVC, motor vehicles or something else, but we also secure that motor vehicle presence. So I'll finish up there. I'll finish and say again, thank you so much to our partners at Rutgers and Tel Aviv University. You've really been key advocates and partners and supporters of ours, and we hope to be that way with you. I can't say enough about what an honor it is to kick this off, what an important relationship. And I'll turn it back over to you, Vince. Thank you very much.
Thanks so much, Director Maples, and thank you for giving us an overview into the efforts that you and your colleagues put in to protect the citizens of New Jersey, and just as importantly, the infrastructure of the state against cybersecurity attacks. It's much appreciated, and thank you for your efforts. I'll now turn to introduce our next speaker, which is the featured speaker from Rutgers University and one of our one of our true experts in cybersecurity at Rutgers. His name is Dr. Saman Zanuz. Saman is an associate professor in the Electrical and Computer Engineering Department at Rutgers. His research has been awarded the Presidential Early Career Awards Medal for Scientists and Engineers by the President of the United States in 2019. And he's also a winner of NSF Career Awards in 2015. Saman's talk today is going to be on trustworthy critical infrastructure via physics-aware and AI-powered software security. Saman, would you like to present to us? Thanks very much.
Absolutely. Thank you, Vince, for the warm intro. You guys can see my slides? Okay. Thank you for inviting me, and I'm so happy to be the third speaker in this series. And as you know, I'll talk briefly about our projects in cybersecurity, all collaborative efforts, and I really would welcome any collaboration that we could actually find together and work together on. So actually make it full screen. Okay, great. So what I'll talk about, as I mentioned, I'll briefly go over some of our projects, collaborative projects on cybersecurity against cyber physical systems, or CPS, in critical infrastructures domains. I'll talk about attacks that have really happened in the past, or our investigations of what parts of the system could be vulnerable to similar attacks in the future. And then on the defense side, talk about how can we defend against these adversarial parties and malicious misbehaviors through offline protections to protect the systems before they go operational, and while they're operating, how to monitor their operation for security and safety purposes. So as I mentioned, our research focus is on cyber physical systems. These are systems that are combinations of physical processes of some sort and computational logic and executions. For example, electricity grids, power grids, a water supply, healthcare, robotics, autonomous driving. These are, for example, robotics. You have the physical process, the robotic arm that is being monitored and controlled by a computer. So that makes it called cyber physical system. And some of these actual transportation, healthcare, or power system, for example, being critical infrastructures of the societies being so important for societal level services, it makes them targets for attack. And it's not just a hypothesis, it has been shown in the past by attacks of coming from different extremes, like a teenager board, for example, turning a TV controller into a train station remote control and causing a fatal train accident and crash, all the way to nation state attacks like malware such as Stuxnet was against critical infrastructures like Iranian nuclear enrichment plants, or many others that came afterward. So this wide range of attacks against critical infrastructures makes them actually very important. US being itself a target of many of such attacks recently and in past years especially. So Homeland Security and other agencies like National Science Foundation have recognized these attacks as a real concern for national security, and creating initiatives and programs, funding programs that actually our research has been funded by. But as essentially the bottom line being that industry of critical infrastructures right now is really needing security solutions to protect our critical infrastructures of different application domains against these sometimes nation state adversarial parties. So talking of cyber physical systems, and specifically, for example, power system, conventional power system, which is a physical process like Kirchhoff laws that you generate power in some generation plants and transfer power through transmission lines to neighborhoods and factories and universities that consume power, so-called loads. It makes it called conventional power system, which is a physical process. But when we talk about cyber physical aspect of this power system, so-called smart grid, we're talking about instrumenting and enhancing this physical process by sensors of different sort to measure current and voltages in this power system, to send these noisy measurements to the cyber part of the cyber physical system, so-called control centers, where we receive these noisy measurements, run so-called state estimation algorithms to get rid of the noise in these measurements, and then feed it to the controllers to decide whether anything is needed to be done in this underlying power system. And if so, those control actions are sent to actuators, which we also instrument this power system with in this example, like generation controller to say how much power I need to generate, or in robotic arm, like what's the angle that I want this robotic arm to have, or autonomous driving, I want to turn left now or turn right now. And different actuators of different kinds, such as also at the bottom, you see PLC or programmable logic controllers that have been the target of several real attacks in the past that I'll talk about. But the cyber physical system have been shown to be attackable by real attacks in the past and research papers from different angles. That you see some examples on the control side, as well as on the sensor side, where the sensors get infected by hackers, and then they make the sensors to send malicious, corrupted measurements to the control centers to mislead the operators about what's going on in the system, all the way to the control channel, such as Stuxnet and Ukraine attack that made the controllers send malicious control commands to underlying physical process to drive it to an unsafe state. If it's autonomous driving, to make the car crash. If it's power system, to cause a blackout like Ukraine attack did. If it's, for example, nuclear enrichment plant like the Stuxnet case, it made 20% of the centrifuges fail and get damaged. So these are different channels that attackers can target. But specifically about the Stuxnet and Ukraine attack that I talked about, how they really happen, as I mentioned, they target the control channel in the cyber physical setting, where they compromised, actually simplifying the details a bit, they compromise the servers in the control center, the attack, the malware does, and then it makes those infected servers send malicious controller logic to underlying actuators, in this case, programmable logic controller or PLCs. By the way, these images are just for presentation purposes. So they don't actually, we use different tools. I'll actually get to details of that in a second. But the malicious controller logic makes the programmable logic controller drive the underlying physical process to an unsafe state, as I mentioned. So getting into a bit of technical details of these two attacks, Stuxnet and Ukraine attack, so-called black energy. In a Stuxnet case, what they did, they compromised the Microsoft Windows server in the control center and injected a DLL, or dynamically linked library, that you probably have seen the DLL in the error messages in those operating systems if you've used. It injects a DLL, a malicious DLL in the server that they compromise. So when the operator develops a control logic for the PLC and wants to send it over, transfer it over to the PLC for execution, this malicious DLL would intercept that request and replace it with a malicious control logic, so that the PLC will then execute a bad controller program to harm the underlying physical process, like the power system. But when the operator would send other requests, it would, the malicious DLL would just forward to the legit software modules, and they would just take care of it. Black energy, on the other end, the Ukraine attack that happened in 2015, 2016, followed by others, actually caused the blackout in Ukraine. And it used a conventional malware suite, so-called Black Energy 3, that comes with several libraries that you kind of plug and play. You can create your own malware type thing. And specifically, one interesting DLL is the TeamViewer that you see in the list, that would allow the attackers remote real-time access to the control servers while the attack is in progress. So compared to Stuxnet, it was much less autonomous, the Ukraine attack, but Stuxnet was completely autonomous. The malware would do all the distribution, everything by itself without any direct remote control, and it was all well programmed. What we did in our research lab to further investigate other potential vulnerabilities that these systems or programmable logic controllers may have. They essentially got the PLC, as I said, not really shown on the model shown on the slide, but we physically broke into the PLC and found the JTAG pins that would allow us to directly access the processor without having to go through the software of the PLC. So it would get us the direct access to the program, like the processor. Again, these are just looking a bit, may look a bit scary, but all we did was connect these pins, connect to these pins of the processor through so-called JTAG ports, and we were able to read out the firmware from these controllers, the PLC controllers. After making the connections, and then we read out exactly what you just see, which is gibberish looking binary file, no source code available. So we had to do reverse engineering ourselves. All we had that at the moment was just the data sheets from the hardware that would allow us to just get some guesses and make guesses about what different parts of the program may do. But all we had was just scary looking complicated graphs, like function call graphs and different parts of the software that we eventually had to, it took us like 1.5 years to complete this. This was actually an NDSS paper to get it published eventually after making information disclosure, the responsible disclosure to the PLC vendor that we were actually investigating. So after doing all these steps, what we did was essentially to inject our malicious code within the firmware of the PLC. What that allowed us at the high level was to run our rootkit, the malware malicious software, within the firmware of the PLC, which would be running below, it's kind of operating system, a simplified operating system, that would run below the control logic, and that would run essentially developed by the operator on the top. And the whole thing is controlling and monitoring an underlying system at the bottom, as you see, the power system or any other physical process that we instrument by sensors and actuators, as I mentioned. So when on the right-hand side, when the operator or the control logic sends a legitimate control action to the actuator to drive the system towards a safe state, our rootkit within the firmware would intercept that action and replace it with a malicious copy to drive the underlying system unsafe. But the follow-up measurements coming from the sensors would then show that something is going on wrong within the physical process, but instead our rootkit would intercept those as well and replace them with legitimate looking measurements by running a simulation of an underlying physical process. So everything to the operator and the control logic would just look normal about the underlying physical process, while the underlying physical process would be in trouble. We validated this system empirically in a real world power system testbed owned by our collaborators. And as I said, this was an NDSS paper. So that was a rootkit within the software of essentially firmware of the PLC that could possibly be detectable by any security monitor that is doing integrity check of the firmware or the control logic that is running on the PLC. We further explored potential extensions to this work and see if we can implement this malware as a mountable hardware implant on the PLC that could be controlled by cellular network of the attackers. So kind of supply chain type attack where on the top, like actually at the bottom, you see two boards. The small one at the top, TNC board, has our malicious code, and the one at the bottom is the GSM, the cellular network connectable board. That we mounted those. Actually, I'm skipping a lot of details here, but just to give high level view of what the result was. Eventually, this was mountable within the PLC. It could be actually much smaller. This was just a research prototype. But what it allowed us as attackers in this case to be monitoring the PLC maliciously through cellular network connections. So any security software that runs within the PLC to do integrity checking of the software would not be able to detect us. Any network-based intrusion detection that is an industrial control system that is using this PLC would not be able to detect us because we're not using that network. And also we could remotely control what this PLC does, and this would allow us also to make coordinated distributed attacks against the infrastructure that these PLC control and monitor. So a part of our research always in cybersecurity is to investigate potential attacks that could happen in addition to ones that have happened, to proactively come up with defenses against them to prevent them from happening in real world. So from the outside viewpoint, both PLCs would look the same, but the one with the hardware implant would allow us to, as I mentioned, to remotely monitor and control the underlying platform. So moving on to the defense side now, given these attacks, what can we do to protect against these platforms, against such adversarial misbehaviors? The first work that we had on this topic, again, our NDSS work, another paper where our solution, so-called Trusted Safety Verifier, as a bump in the wire device, would sit between the control server computers and the PLCs. So any control logic that is sent by the control center operators for execution on the PLC would be intercepted by this Trusted Safety Verifier. And Trusted Safety Verifier, going through a lot of steps of programming language techniques and formal verifications and model checking, would analyze this control logic first to make sure that that will not cause underlying physical process to go in an unsafe state if it is let run on the PLC. Once it's vetted, then the control logic will be allowed to pass through and go for execution on the PLC. Otherwise, it will be sent back for to the operators through a different channel for intrusion detection or debugging purposes. We also implemented a similar idea on additive manufacturing, and that we have actually another collaborative work with Georgia Tech, and this is under submission, where the design files are sent to get printed by the 3D printers, but our trusted integrity verifier in this case would intercept those designs to analyze if they have not been tampered with, for example, to inject voids within the object. Once printed, for example, imagine this is a propeller for a drone. If it is injected by like a void, for example, it would break while it's in operation. So to prevent such attacks from happening, our solution used deep neural networks to classify what type of object is going to get printed, and then do analysis of to identify weak structural points of this design before it gets printed, and then do finite state element analysis, finite element analysis to figure out if any part of this design has really been tampered with maliciously before the design is sent to the printer for print. In another Unix paper, what we did in this 3D printer domain was to inject golden nanorods within the filaments of the printer before the printing happens, and calculated or predicted where these golden nanorods should show up if the printing process goes on correctly without any malicious intervention. And once the printing process finished, we get the printed object and perform a CTS scan of that object and locate where the golden nanorods are located and compare it to our predictions of where they should be located. And if they are located in the correct places, then the printing process is vetted and the printed object can be used in whatever, for example, as a propeller in the drone or a wing of an airplane or anywhere that's been purposed for. So moving on to the online defenses, these are solutions that we could use when the system's in operation to perform encryption or security monitoring of the systems to make sure that attacks don't happen while the system is on operation really. On the sensor part, before the sensor measurements are sent to the PLCs, we designed this trusted sensor base, which was actually a best paper award in IEEE Smart Grid.com, where the analog signals at the data acquisition points of the sensors are encrypted before even they are processed by any digital components of the circuit board, such as analog to digital conversions or any of the transfer. modules on the board. So anything that can be hackable or infected remotely by the hackers would see the signal after it's gotten encrypted. So that would actually raise the bar for the attackers to see any of the actual measurements coming from the system. But once the sensor measurements are received on the PLC for processing, so the controller may also get infected. So we have to do security monitoring of this controller to make sure that it is doing the correct job, it is running the correct software, and it is calculating the correct outputs for the actuators. What we did in this project was to create a replica micro neural network of the control logic on the PLC that does similar job in terms of calculating output from the inputs, but in an approximate computing fashion. It's not supposed to replace the actual controller because there's no optimization going on. It's not accurate, but it is just there to make sure that the controller outputs are within the correct range of what they should be based on their inputs from the sensors. So this replica model, we would run it in parallel, and that would allow us to do online security monitoring to make sure that this controller is doing the right thing. So attacks like a Stuxnet would essentially be detectable by this solution. Last project that I would like to just touch upon is our CCS paper, actually in this case, side channel based intrusion detection or attack detection of these controllers, where in an air-gapped fashion, we monitor different side channels of these controllers, for example, thermal side channel, to see which parts of the processor are heating up when the control logic or software is running within it. And we also went through different modalities such as electromagnetic emissions of the processor, as well as acoustic side channel using this laser vibrometer to see which parts of the processor is vibrating, like nano vibration, and can we use those channels and signals to figure out what software is running within this processor in an air-gapped fashion. So we are not running any security module within the processor. So the real-time operation of the PLC is not being affected, and any attack that happens within the software will not have access to our monitor to kill it possibly. Finally, we were able to find the best modality, which is electromagnetic side channel, that, as shown in this frequency spectrograph, different instruction types in the software that is shown on the right is giving us different fingerprints in the signal that we receive from electromagnetic probes. And we use those to figure out and detect if the controller is running any malicious software successfully. And the details, again, is in our CCS paper on this. That said, I will actually conclude. And actually, we will keep Q&A to the end, but I would just to reemphasize again that my goal here was to go over different projects that we have going on. And we really, I really welcome any kind of collaboration that you guys could think of on these efforts. I would, almost all of them are collaborative efforts. Thank you. I'll give it back to Vince.
Thank you very much, Saman, for your presentation, and thanks really for all your hard work and coming up with solutions to frustrate cybersecurity attacks both now and in the future. And as you indicate, one of the reasons that we were brought together by the commission, the New Jersey Israel Commission, is to engender collaboration between Tel Aviv University and Rutgers University on important topics like cybersecurity. Next, I'm going to introduce Dan Peer, who will then introduce the featured speaker from the Tel Aviv side. Dan has been a good partner over the last several months in bringing together these joint symposiums. He oversees the Spark Innovation Lab at Tel Aviv University and has also served as the Vice President of Research and Development at Tel Aviv University. Dan, floor is yours.
Well, thank you, Vince. It was very interesting. I'd like to take this opportunity and thank all our speakers anyhow, but first I want to introduce Eran Trumer, who is a professor, associate professor in Tel Aviv University School of Computer Sciences, where he heads the lab for experimental information security. He's also the co-director of the Checkpoint Institute for Information Security. Eran received his PhD in the Weizmann Institute of Science, and still we love him. And previously pursued his research at MIT and in Microsoft Research. His research area is cryptography and information security, focusing on risks possessed by physical attacks and untrusted platforms, from perspective spanning the full spectrum from theory to practice implementation. So thank you, Eran, for being with us.
Thank you for the introduction and for the honor of being in the symposium. This is a wonderful opportunity to explore several facets of modern cybersecurity and its challenges. And I especially appreciate the opportunity to talk after Saman and complement his perspective, in the sense that we just heard about very powerful techniques for defense through physics. And I would like to talk about attacks through physics and defense via cryptography. I head the Laboratory for Experimental Information Security at Tel Aviv, and we have many branches of investigation under that umbrella. It includes analyzing vulnerabilities at the physical level as well as the software level, using advanced tools such as machine learning in order to perform attacks and analyze their own vulnerability. And we also do a lot of system building, try to understand how we can build secure systems that defend against the attacks that we and our colleagues have found, as well as the one that we encounter daily in the newspapers, and try to build more robust computing platforms. There are too many topics to cover comprehensively, so I try to build this talk in a way that will touch upon many hot areas that we are working on and that are opportunities for collaboration. And I will exemplify this through several specific lines of research. And the first one is side channel attacks, a specialty of our lab, exploring the applicability of side channel attacks, that is, inadvertent information flows from computing devices. And in particular, understanding whether they are applicable to common computing everyday devices like laptops and desktops and cloud servers that we are relying on. One of the first, maybe simplest attacks that we carried out in our lab is the study of acoustic side channels. Simply speaking, the noise made by electronics as they're doing their thing. The voltage regulators struggling to stabilize the voltages and currents that are then fed into the CPU and are therefore manipulated by what's going on inside the CPU. Some of you working on your computers late at night in a quiet environment, hard to imagine these days, but it happens. May have noticed strange buzzing noises. Well, it turns out that these convey a lot of information about the content of the computation. Sometimes you can even hear them by ear. Of course, you can hear them a lot more with dedicated lab equipment. So here's a simple setup. We have a filter amplifying, digitize the information. And what we see is intriguing. We see that there are changes in the acoustic noise generated by that laptop. And if you run something sensitive, like a cryptographic computation, in this case, RSA signatures using a secret key consisting of two secret numbers, P and Q, you can actually look at a time frequency representation of this signal and observe the changes between these two secret components. And from that, with additional analysis, you can even deduce what those secrets are and therefore steal those signing keys and impersonate the person who owns the laptop whenever they are entrusted to sign information. Whoops. So these kind of attacks, as you just saw, can be done in proximity. They can also be done at a distance, in this example, up to 10 meters away using a parabolic dish. And they can even be done sometimes using the built-in sensors of other machines nearby. For example, just a simple cell phone placed nonchalantly next to someone's computer can steal the secrets within that computer when they are affecting ongoing computation. So this is something that was very surprising. The publication came a decade later, and then we went back to declassified NSA publications and other sources, and there was no hint that people were aware of this attack vector insufficiency. And that got us thinking about what other subtle exploitable information flows there are from these everyday devices. And figure out that electromagnetic radiation is also obviously a potential vector, and it was extensively investigated in other contexts for simple devices like smart cards and microcontrollers. For or not in a way that is useful. So as you can see in the picture, even simple improvised devices can acquire electromagnetic signals. You can analyze these, you can find a carrier, you can do the modulation, subsequent analysis, and you end up with cryptographic keys. Even simple touch, just using your hand or pen as a conductor, can capture electromagnetic fluctuations in the potential of a device and yield secret keys and other sensitive information. But that's not all. It doesn't have to be all physical. Some information is leaking by the side channels at the network level. For example, here is an important research problem that we are all grappling with probably this very minute. You see your colleagues on Zoom, and some of them seem somewhat distracted. Now, is it because they are pondering the deep insights that one is conveying, or is it because they are reading their email? So clearly highly motivated, and I'm glad to report an important breakthrough in this applied research. It turns out that you can tell what they're looking at by listening to the audio that they are conveying on their voice over IP call. The audio that they're sending, when they're not muted at least, it contains their speech, the ambient noise, but also some subtle fluctuations injected by the electronics inside the computer, which are conveniently adjacent to the microphone and its circuitry. So we can actually record these by any variety of means. For example, maybe through a cell phone, a smart speaker, the built-in microphone and a webcam. Any one of these is sufficiently sensitive to pick up the acoustic noises or electromagnetic radiation that induces acoustic noises as picked up by the microphone. And that can be analyzed and used to deduce what we're looking at. You can sort of look at it just by eye for very simple images. You can find some time domain correlations. For deeper analysis, like distinguishing applications and websites, is it email or the Wall Street Journal? Well, that requires some heavier machinery because the noise is so indirect and has very high variability. So we threw the book of machine learning at it, and we used some signal processing followed by convolutional neural networks, leading to the ability to distinguish between websites, between voice displayed on the screen if it's in a sufficiently large font. So taking a step back, side channel attacks are really dangerous, not just for small devices, but for anything that has sensitive context such as cryptographic keys or the human behavior or anything else that computers convey. And this may leak by acoustics, by electromagnetics, if someone has physical access, then by probing, through power analysis, optical emanations through suitable access. And another very hot, very fruitful line of research is leakage through a computer architecture. Whenever you can run some code on a computer, you can observe how other code running on the computer interacts with yours, induces subtle delays and behavior changes in your own code, and that can cause leakage of sensitive information. It goes back to our work in 2004 on cache contention attacks. Recently, you probably heard about Spectre, Meltdown, and many other extremely powerful techniques. We've seen dozens of papers published every year that show how weak is the infrastructure on which we are building everything in terms of its ability to compartmentalize and contain information flows. And strikingly, you may say, okay, maybe all of these require people to have physical access to the computer, so I'll just keep them away, 10 meters away, so they can't even do acoustics. I close the windows so they can do laser vibrometers, as Samantha alluded to earlier. I'll keep them maybe off the internet, so forget off the internet. I'll keep them I will forbid any code execution by potential adversaries to whether it's by code execution that is as supposedly benign as JavaScript code running on your computer that can manipulate its states and make observations, or even exploiting built-in sensors like the microphones inside your computer. And in an ongoing work, we show that just the built-in sensors conveyed through voice over IP channels are enough to, for example, exfiltrate cryptographic keys, as well as even more insidiously cheat in Counter-Strike games. So to take a step back here, a high-level lesson that we ought to learn from the repeated discovery of such attacks is that computers are just broken in terms of their fundamental hardware and low-level software architectures. They are really deeply incapable of ensuring the integrity and confidentiality of data and computation, especially if you deal with general-purpose devices that are optimized for performance. And so if the computers are just inherently faulty and leaky, what can we do? How can we develop general theory and tools for protecting against general attacks, as well as protecting specific critical applications? And this is where I switch over to discuss the wonders of modern cryptography, the recent renaissance of cryptography. And I'll exemplify this by a particular technique, zero-knowledge tools, motivated by a particular application, zero cache. This application is motivated by Bitcoin, blockchain. Bitcoin introduced the idea that we can do decentralized computation, in Bitcoin's case, tracking cryptocurrencies, without trusting others. How would the identity of the parties involved is put on the blockchain for everyone to check. And that enables the checking of integrity, as well as detecting if someone is trying to double spend their coin and thereby cheat. The cost of that is privacy. Because everything is on the chain, identities can be tracked. Consumer purchases can be identified by friends, neighbors, and coworkers. Account balances can be seen by anyone that you transact with and knows your address. If you're a merchant, then your cash flow and transactions are exposed to a competitor. If you're a nation, then your citizens' transactions are exposed to your national adversaries. That won't do. That is a very weak foundation for building a distributed computation platform on. And so we built something called zero cache, which is a privacy-preserving on anonymous blockchain that uses zero knowledge proofs to hide the information by having a blockchain that consists of essentially encrypted blobs of information, which users can still verify. And while the parties to a transaction know the content, and the tools for that is cryptographic proofs. Instead, when the sender of a transaction wants to convey integrity of the recipient, which is a privacy issue, they instead invoke sort of a virtual accountant that checks the transaction and produces a signature or attestation of the correctness. Except that this virtual accountant is a computational object, is an algorithm that can produce a proof that can be checked cryptographically by the recipient, as well as anyone else on the chain. And projects. In recent years, there has been an amazing surge of discovery, both theoretic and implementation of such proof systems. This is a very partial list. I ran out of slide space very quickly. Our own contributions include, for example, the eavesdropping library, which is a very popular implementation of zero-knowledge proofs, as well as several applications, for example, the zero-cache one I'm describing now. So this started as an academic paper, a collaboration with several authors, and then we decided to actually deploy this in a real-world cryptocurrency called zk-SNARK. Started with a very small team, launched in 2016. It's started with, this is the node network on the launch day. You can see how eager people were to see the technology working. And it very quickly grew very much beyond this. These are recent statistics. We're seeing tens of millions of dollars transacted every day, dozens of exchanges and software developers, a very vibrant ecosystems, copycats that forked our code. But most excitingly, in the current context, we're seeing novel research driven by this. We're seeing major cryptographic advancements and motivations for basic research and many research papers in top venues coming out from my colleagues and me and many others that now recognize new needs, new challenges, new trust requirements and security requirements, and build up these cryptographic tools. So we're very excited about facilitating both the privacy as well as the research. There are many other applications. Time won't allow me to discuss any of them at length, but I mentioned that this can be extended far beyond simple smart contracts. It can provide scalability for computation on the blockchain. It's used by JP Morgan and Ernst & Young for private asset tracking. Your knowledge combines nicely with the trusted sensor base from the previous talk. We should discuss that. And there are even defense applications. Recently, DARPA and IARPA had 3 different programs, a current one, SIEV, and 2 recent ones, Verona and Hector, all of which had zero-knowledge components to defend high security national applications. By the way, this is just the most recent physical ZKProof standardization workshop that I call it. The most recent one was unfortunately a bunch of people on Zoom windows. So you can judge the merit just by some of the names and faces. I also mentioned that my zero knowledge here was just one example of the maturing mega cryptography tools in the cryptography renaissance. We have other tools that are very powerful, like zero knowledge in the fully homomorphic and many other things that are extremely powerful in expressing properties. And we are providing a powerful vocabulary for the things that can be enforced cryptographically. And therefore, the challenge that I would like to pose to the people in this room and well beyond is, what should we use this vocabulary for? We have the words. You need to write the poems about your security needs, about how the applications can use these tools to ensure concrete properties that would solve the real world problems. This is an amazing opportunity for collaborations. We have many such projects going on. Please talk to me about anything that you think this could be applicable for. And without further ado, I will pass on the baton.
Thank you, Eran, for that excellent overview and presentation. I guess among other things we've learned, for future Zoom presentations you make, we need to make sure to pay attention, because you can tell the difference whether we're listening to you or watching our Facebook page. So thank you very much. I'm now going to turn over for questions and answers. Tom Farris to moderate. Dean Farris has been the dean of the Rutgers School of Engineering for the last 12 years. Before that, he headed up the School of Aeronautics at Purdue University. Dean Farris, would you please moderate the Q&A? Thanks very much.
Yes, it's my pleasure, and thank you to both of our speakers. Those were quite extraordinary presentations. For Professor Tromer, one of the things we're grappling with at many universities in the US is this point about being able to observe people in a Zoom meeting and thinking about students in classes and students during exams and how do we sort of balance putting them in high pressure situations and being able to monitor what they're doing when they may have, for instance, here, younger siblings in the room next to them and so on. I'm just sort of curious about the Tel Aviv experience with
Tel Aviv, we certainly had our own share of excitement in this regard. It's difficult to find the right methodology here. Frankly, I have been fortunate to not be teaching this semester. So I'm mostly looking over my colleagues' shoulders and trying to learn from them in order to avoid some of the perils. Clearly, one needs a well-honed remote instruction infrastructure that tends to have amusing interplays with the existing infrastructure and institutionally mandated technology. One also needs realistically to extend some trust to the students and realize that those who are in it for learning will be able to make the most of it. Those who are intent on cheating may be able to foil the quantitative measures. And I think that in the years to come, as we evaluate this generation as employers or advisors, we will have some challenges.
Thanks, very good. So, and Saman, for you, one of the, you're lots of things about the integrity of the power grid, and my sense is that as repairs are made to the power grid, the owners don't actually have a clear sense of what the network looks like, and maybe this is down at a local level so that it's so small that it's not really an issue. But I'm just curious about your comments there.
No, that's actually an excellent point and actually a very valid point. The traditional power grid, when it started like a century ago, it was very centralized system where the generation plants were just very recognized and then people would just be able to consume. But now with renewable energy and more distributed energy sources at the distribution levels, the system is, yes, as you mentioned, less observable and hence less controllable from a centralized viewpoint. But as research has shown, actually, it makes the system more resilient against attacks in some sense because different parts of the system are able to compensate for any kind of failure or misbehaviors that may happen in some other parts, because now we have more generation, more but distributed, which actually makes the controlling of the system, monitoring control the system from the high level viewpoint more challenging, but it makes the system more resilient. For instance, one of the early attacks that were that was shown to be very practical, but advanced metering infrastructure where the smart meters were distributed. It showed by these smart meters making like wrong claims about the generation and like the generation, household generation and the consumption. They could be they could possibly affect the stability of the overall power grid. But now with renewable energies, research has shown it's not anymore possible because whatever they do, more distributed resources around the country could cope with it possibly. But would they in practice? There's been no real attack to show that. But attacks such as the Stuxnet or like, for example, Ukraine attack, these are targeted attacks that they do a very good job at their reconnaissance and knowing the infrastructure and then targeting the systems. Again, also against US facilities has been attacks. So like defending against those attacks are very difficult, but 99.9% of the attacks are not targeted and they're less difficult to be defended against.
Thanks. That's very interesting. So I think this question is more for Professor Kromer. And it's really sort of an example of how we can get pretty far along and forget how complicated this is for the general audience. So the question is, what is blockchain technology, and what is the very basic principle behind it?
Yes, that is a question that we explore at length over a full semester course. The reason this is nuanced and frankly confusing is because there is a lot of conflation, often intentional, between several different concepts that make up the blockchain terminology. The core of blockchain is achieving distributed consensus on a state of a system through a decentralized public ledger that anyone can observe in order to ascertain the current state of the system. And there is some mechanism for extending it in a way that ensures consistency. A popular, and the first example is Bitcoin, where the blockchain is maintained and extended by so-called miners that earn the right to extend the chain with any valid new information by solving mathematical puzzles. And the information conveyed on that blockchain, in the case of Bitcoin, happens to be transactions in an asset. This nicely generalizes in many ways. You can represent other kind of content than asset transactions. You can think about other ways to extend the chains through other computational mechanisms and protocols. And you can address matters of privacy and scalability. And most powerfully, you can have it represent a powerful computation, so-called smart contracts, rendering it into a global, consistent computer that anyone can interact with. And Ethereum is an example of
that. Thanks very much. Another question from the audience, which is very timely, is have either of you studied the manufacturing systems in the cold chain? So in addition, so how do we make sure that the vaccines that are getting distributed now are actually what they say they are?
I probably can take this. Two efforts we've had in this topic. One is actually related to this topic. One is 3D manufacturing that has been for PPEs, the personal equipment like masks that are used against COVID vaccines recently, and have shown they could possibly be, even with regulatory guidelines by the government being enforced, they are possible to be attacked through remote cyber attacks, such that very thin air gaps could be introduced within these masks, not observable, to make them essentially ineffective against protections of the mass, like actual virus distribution and infections. Another effort that we have had related to this topic is cybersecurity of CRISPR technology in biology. And we worked with New York Genome Center on this. So CRISPR technology that probably many of you already know, that has received like Nobel Prize, Professor Doudna from Berkeley and Charpentier from Max Planck, is about being able to modify the DNA and receiving a DNA copy of any organism, actually, for example, human, and being able to modify any part of the DNA, any nucleotide that you want, cutting it, editing it, inserting any new addition. And a lot of this, the whole chain, the process of CRISPR is done through software. Essentially, you have to first sequence it and try to figure out essentially what nucleotides are there, and then design the so-called guide RNA, which is the scissor there to cut. And then essentially mix them together and then cut, and then monitor if the cut was correct. If it was not, it didn't cut some off targets, off sites, or like the correct place is cut. So if any software in this chain is infected, possibly if this CRISPR is used for therapy that has been in practice, could possibly just be ineffective in curing the disease, but instead possibly can affect some other part of the DNA, that some proteins are not anymore transcribed or translated correctly, and hence disease may come up as the result of this maliciously actually corrupted process of CRISPR to change the DNA incorrectly. And I'm sure the same thing would be for vaccine production, but that has not been our target. But this CRISPR we have worked on this for the over last 1.5 years. It's actually very exciting.
Speaking of exciting, I'd like to fall into the habit of complimenting what you say, Saman. You spoke about defending the biochemistry. We actually have new work on defending using biochemistry.
Nice.
In collaboration with Tel Aviv's immunology department, we are showing that some problems that are notoriously difficult for biologists and biochemists, and even for the immune system, if one indeed believes their difficulty, then, well, what do cryptographers do with difficulty? They try to distill it into the difficulty of computational problems, and therefore build new encryption schemes and other cryptographic objects that are at least as secure as solving the problem. So the cartoon version of what we're building is a new physical encryption scheme, such that either it's secure or you can cure disease. So, right, we're not sure which one, because we're making an assumption that curing that disease is difficult, but that is a nice way to encourage research that is a win either way.
Very cool.
It's very good to see the interaction between the two of you. So I hope we can somehow continue that. There's a question about what do we teach and what's the curriculum? You know, even starting in high school, right? For kids that are 14, 15, 18 years old, and in college, and so on. Just how do we get this out to the community?
All right, do you want to take this one? I can take, if you'd like, I can take more.
Sure. So I think, I mean, by observing my small sample in between supporting their Zoom access, as well as observing the students that come in, I think that one of the challenges that we have is that consumer devices have become so streamlined that they are hiding the internals. And it is very difficult to break these abstraction barriers and teach kids, as well as new students, what is going on underneath the shiny plastic and glass, and what are the fundamental architectural and theoretical foundations. Back in the day, it was much easier to make the connection between a pixel on the screen or a character to a memory address and the algorithms that drive it. And today, through the layers of abstraction of JavaScript and the SDKs and Scratch, people can get some of the high-level concepts. Clearly, algorithmics has been amazingly supported by Scratch. But when it comes to understanding the threats that we are studying, the information security in particular, cybersecurity, it requires a deep view that cuts through all of those abstractions. And half my papers came from looking at abstraction and saying, nah, that's not really right. Let's see how we can break it and what we can learn from that. So we need the right methodology to expose students to these nitty-gritty without losing them along the way, without making this something mechanical and boring. And I think that some buzzwords are favorably conductive to that. For example, blockchain. Everybody wants to do blockchain. There's money and newspaper articles, whatever. It's a great way to attract them. Because if they want to learn blockchain, then that means they want to learn the distributed systems. It means they want to learn cryptography. It means they want to learn operating systems and networks. And by God, I got some really good students engaged that came for the wrong reasons, but stayed for the right ones.
Actually, to add on that, I would like to also mention that Exactly what you mentioned, Aaron. But also the fact that the students, high school students that I've experienced, they like exactly these buzzwords, but also the excitement that they receive from these potential events that we actually are organized. So for instance, like we have done like hackathons, drones, for like hacking drones for high schoolers at Rutgers, and actually more than 200 students, for example, attended. And some of them were so excited that afterward, we reach out to them, they reach out to us. So we started this weekly meetings with high school female students of New Jersey, one of the schools, and we've had that weekly meetings going on. And I've actually been giving talks in their high school. And so happy to see, like, for example, they got admitted to Rutgers, UC, and Cornell as the result. But the fact that another point that I want to mention is the funding agencies, the way they encourage the faculty also plays a big role. For example, David Corman, the National Science Foundation, my program director for CPS program, he always like mentions this reach outs for educational efforts, and that encourages us to do so really. But also he takes it all the way through industry transitions. For example, efforts that Iran has successfully done in his research, and we've done for PLC with Siemens adoption, our security protections. So all the way from K-12 education, university, and then industry transition really should be in place. Otherwise, just having papers, like doing our research in our lab and publishing papers, is valuable scholarly, but will not impact the society until it really hits at either educational channels or industry transition channels.
So another question from the audience has to do with new things that are coming and how they might impact what you're doing. For instance, quantum computing and what impact that's going to have on cybersecurity. Okay, you're both laughing. Very good.
Aaron, do you want to take this one?
Okay, I'll take it.
Yeah.
Sure. So quantum computing is intriguing. It's philosophically fascinating. It has very deep theory that goes well beyond computation. It's the nature of a universe. What's a fabric of reality, as a famous book is called. But its applications to cybersecurity, as they are currently understood, are mostly in the realm of cryptography. And by which I mean the following. There are basically three famous classes of algorithms that are most significant from the cyber perspective. There is the so-called Grover's algorithm by Grover that enables you to basically, in our context, find passwords harder. Make it easier to find passwords, making it necessary to make passwords harder to guess. Okay, so we'll need to make passwords twice as long. Boo-hoo, we'll survive that. Let's put that aside. There is a quantum key distribution. This is on the constructive side, not an attack, but an opportunity. Pursued, but is it solving a real problem? Well, not if you believe that, that modern cryptography is secure. But is modern cryptography secure? And the answer to that is this is where the real challenges are, because a lot of modern cryptography, all of the common public key cryptography, by which I mean signature schemes, many of the encryption types that are used daily on the internet, will succumb to a different quantum algorithm called Shor's algorithm that really just completely breaks them in the following sense. Once we have scalable quantum algorithm capable of maintaining thousands of bits in sufficiently reliable superposition, then all of those cryptographic tools relying on discrete logs and hardness of factoring would just disappear in the poof of quantum computation, and all of those systems will be broken. And so many cryptographers right now are scrambling to find viable alternatives that do not have any known algorithm, quantum or classical, that would break them. And this is the really hard part, are sufficiently efficient to serve as a drop-in replacement. And there's actually a competition run by NIST, as well as a lot of other activity to choose the best such algorithm, and already some experiments by Google and others to integrate them into deployed protocols. No one knows when that will happen, when these scalable quantum computers will actually become a practical threat. Some say a decade, some say it's always a decade. But we have to prepare because deployment is very lengthy and painful. So I'm very happy to see that some of the recent proposals are very appealing as essentially drop-in replacements. And for anyone watching these recordings, yes, there are many additional things in the realm of quantum computing, like the game theory implications and the protocols that come out from that. I think those are at present less directly impactful on real-world physical systems.
Eran addressed it so well. Nothing on my end, though.
So speaking of that, you must be part of very large communities, and I'm just sort of curious about whether Saman and Eran, were you aware of each other before we put this symposium together, and sort of a follow-on to that? What would be unique about a Rutgers Tel Aviv partnership that would allow the two of you to progress even further in your research?
This is easy, actually. I can take this one. I've actually definitely heard of Eran's work in the past. I've not interacted directly with Eran. I'm so happy to have heard Eran's research. A lot of connections in a synergistic way I felt in terms of complementarity of what we do from the theory and practical aspects, as well as relations in the side channel from perspective. Definitely, Eran, I'll reach out. But I'm so happy that we did this. Yeah.
Second that, and I think that this kind of synergy and indirect channels between people solving complementary problems, as we repeatedly found during this call, is extremely important, especially these days when we have all accustomed to having ourselves and our students remotely collaborate. I'm eager to explore this collaboration.
Vince, I think that's a good one to start to wrap up our Q&A and go out with thank yous to the leaders from Tel Aviv University and the leaders from New Jersey Homeland Security. I also saw we had some participants in other universities in New Jersey here, and happy to include them in our partnership with Tel Aviv University as we go forward. So thanks very much for putting this together, Vince, and thanks Saman and Eran for your time and effort in getting this going. It was very interesting.
Thanks so much, Dean Ferris, for moderating the Q&A and the exchange back and forth from Eran and Saman. I want to thank both of you for the wonderful presentation. Many thanks to Dan Pierre for connecting us with Eran, as well as to Director Maples for the welcome. I thought it was encouraging that there's a lot of not only work going on the state level, but support between the state and the universities in New Jersey. I did want to answer another question that was on the Q&A. We will present video recordings of this symposium. They're also up on the internet, the two previous presentations. So if anyone's curious in the audience, we have recorded this event, and not only this event, but the prior two joint symposium between Rutgers and Tel Aviv University will be available, and we'll send a note out to you on how to get to those. Thank you all very much. Look out for the notice. I believe the last week of February, we'll have another joint Tel Aviv Rutgers Research Symposium. But many thanks, and enjoy the rest of your day. Thank you.
Thank you. Thanks, Saman. Thanks, Eran.
Bye-bye.